Certainly. Here's the passage with punctuation added. Without precedent for the historical backdrop of current mankind, the attractive North Pole leaps toward the South Pole, as well as the other way around. Our reality will be topsy-turvy for some time, and researchers are fastidiously trying to figure out what the looming attractive post-bounce will mean for the Earth. What is sure is simply that the advancement can presently not be halted. The signs are disturbing, and the pole shift may have already started. Attractive post shifts, otherwise known as geomagnetic inversions, have happened quite frequently in the history of the Earth, though on land timescales, so that the peculiarity is normal for the Earth but an extraordinariness for us humans. Attractive pole inversions probably happen overall every 200,000 to 300,000 years. The last finished post inversion occurred about 780,000 years ago. This inversion, known as the Brunhes-Machiyama inversion, happened an unusually long time ago. Better late than never, researchers express the following pole inversion might have already started. If the attractive North Pole leaps toward the South Pole and the other way around, the world's attractive field alters emphatically in the direction of the leap. It even shows extreme shortcomings for a specific time frame. During this time, our human civilization is exposed to an increased risk for solar storms. Normally, the attractive field dependably blocks the molecule streams from the sun, but when it weakens, more charged solar particles can enter into the deep layers of the Earth's atmosphere and potentially cause damage. If we then also experience a peak in solar activity, as is currently the case, it could turn out to be truly risky. Specialists caution that a tremendous solar storm could incapacitate our whole current development. The length of a pole shift is 1,000 to 10,000 years. It sounds shocking and fascinating simultaneously. A pole shift means a total attractive inversion of our planet. North becomes south and vice versa. We humans have never intentionally experienced this cycle, and we don't have the foggiest idea what a pole shift will be like. It might feel like nothing changes, or we might experience significant disturbances and potentially huge failures of technical gear. The attractive field isn't significant for us humans to live or consider this. The impacts of the Earth's attraction on us humans have barely been investigated, if at all. Researchers expect that creatures use the attractive field for direction, and as already mentioned, the field protects us from the solar particle streams. These flows wouldn't be an issue for the globe, regardless of whether they happen at longer stretches and in concentrated explosions. That's because, again, it's our advanced human culture that is in danger due to our reliance on technology. Creatures and the planet itself can generally endure such changes quite well. A pole shift is most likely not an unexpected cycle. It might happen over 1,000 to 10,000 years. During this time, the attractive field weakens and becomes more tumultuous, with the poles over and over shaking or wandering sporadically before realigning. Pole jumps happen as a result of changes in the flow patterns of the liquid metal in the inner core. This is where the attractive field is produced, by an impact that researchers call geodynamo, affected by thermal convection, the rotation of the Earth, and perhaps other elements from space. The extremity of this geodynamo changes, and the direction of the poles changes with it. Current cycles in the Earth's attractive field are disturbing. The Earth's attractive field is currently changing in a momentous manner. Throughout recent years, the attractive field has lost around 10% of its strength. It is seen with concern that the attractive field continues to lose strength, and the pace of this decrease seems to be increasing. For quite a while, there has been a region with a harshly debilitated attractive field over the South Atlantic. This irregularity is growing every day, and in the most pessimistic scenario, it will spread to form a huge hole around here. Satellites and electronic gadgets are now increasingly exposed to enormous radiation, and no one knows where this development will lead. In the north, weird changes have been seen since the 1990s. From that point forward, the attractive North Pole has been moving increasingly fast. From a couple of kilometers each year, the rate increased to around 50 to 60 kilometers each year. Right now, the attractive North Pole is moving toward Siberia. This still sounds incredibly northern to us, but there is an impressive distance between the original North Pole and its current position. Researchers recognize a few poles. Our Earth has a North Pole, which, measured along the Earth's axis, is practically constant. Despite the fact that our planet has encountered pivotal changes in its history, these events are less frequent than attractive inversions. Obviously, our globe also has an absolutely land North Pole at the top of the northern side of the equator. The attractive north is determined by the pure revolution of the Earth's attractive field. Traditionally, all of these poles digress somewhat from each other and don't lie exactly together. Simultaneously, at one point, the attractive post is the most dynamic, and it meanders the most. The attractive field doesn't wrap our Earth statically, it courses and varies. A phony problem is, are we encountering a superchron? A few researchers are distrustful. Are we truly confronting a post shift, or is it all manipulative? The last shaft hop around quite a while back was quite a while back, considering that such occasions happen on average every 200,000 to 300,000 years. Researchers suspect that such periods without a post-hop are similarly as ordinary as patterns of a few hundred years. There have been evidently works in the Earth's history in which no shaft hop happened for a few million years. Specialists allude to such stages as superons, and we could be in the center of one of these periods. During the Cretan superon, the Earth's attractive field stayed stable for around 30 million years. We could right now be in a comparable, yet more limited stage. The quake of the North Pole would then be a typical variance and not an indication of a total jump. The explanations for an abnormally lengthy solidity of the Earth's attractive field could be geodynamo components. The external planet center could be in a especially steady stage, by which the stream designs in the fluid iron are presently barely upset. Some specialists convincingly contend that geomagnetic inversions are tumultuous and hard to anticipate, so lengthy stops are normal. They express that without additional proof, it's unrealistic to with certainty predict a post-inversion for the following 10,000 years. What might a post-shift mean for our civilization? During a shaft shift, the Earth's attractive field will debilitate, which could imply that the Earth is briefly less safeguarded from radiation from space. This could debilitate nature and maybe additionally our bodies. In some ways, the specific impacts of a sharp decrease in the attractive envelope of our planet have not been adequately explored. Anyway, the fact that technological frameworks makes it sure, like satellites and correspondence organizations, would be disturbed by the radiation. In addition to interruptions to correspondence frameworks, we could experience blackouts. It's conceivable that more creatures will wander into regions where they don't have a place. Whales grounding themselves on shores is similarly possible, as is large groups of birds getting lost. No one knows how rapidly creatures will adjust to the new circumstances, and whether their inside route frameworks may adjust all the more rapidly to the new direction of north and south than our systems do. The degree to which a post-shift would influence the climate and environment is at present the subject of warmed banter. We essentially don't have any idea what would occur if the attractive south turned into the attractive north, as well as the other way around. What is sure right now is just that a post-shift would represent an extensive challenge for our super-advanced society. Researchers are right now checking each change intently with the goal that they would be able to survey potential dangers at an early stage. How did the Earth's attractive field come about? It's really a supernatural occurrence. The Earth's attractive field empowers our planet to have a climate and, hence, permits us to live. Planets without an attractive field, for example, Mars, lose their environment, if they ever had one. The geodynamo inside our planet is subsequently a genuine fortunate turn of events. Inside the Earth, the revolution causes electrically conductive fluid metal to be shaken this way and that, making attractive forces. The Earth's core comprises of a solid metallic internal core and a fluid external core. Iron and nickel in the Earth's inner layer are liquefied by extreme heat from the inner core. A kind of convection current makes the fluid metal circulate like bubbling water. The fluid iron is conductive, and its development produces electrical flows. These flows, in turn, create an attractive field. The Earth's turn forces these convection flows into twisting patterns. Researchers know this impact as the Coriolis force. Once created, the attractive field enhances the developments in the fluid metal, making a steady cycle that maintains the geodynamo. The outcome is a global attractive field surrounding the Earth like a giant bar magnet, forming attractive north and south poles. These cycles have been well informed and potentially made sense of by science. Regardless of this logical order, our attractive field is a logical supernatural occurrence. It seems perfectly organized, and without it, our reality wouldn't be what it is. The magnetosphere safeguards the Earth from the solar wind. The Earth's attractive field redirects the solar wind so it can't directly impact the planet. The solar wind literally compresses the attractive field on the side facing the sun. On the side facing away from the sun, the solar wind extends the attractive field, making a long tail known as a magnetotail. Notwithstanding this practically awesome defensive safeguard, the Earth gathers larger amounts of solar particles at the north and south poles and ties them in pocket-like fields. These regions were named after their pioneer as the Van Allen radiation belts. In 1958, the astronomer James Van Allen saw for the first time how charged particles of the solar wind are caught and packaged by the attractive field. Once caught, these particles travel along the attractive field lines from one pole to the next, gradually losing their charge. The internal layers of the Earth's atmosphere hence remain perfectly safeguarded. If particles do figure out how to escape, extreme conditions like the Carrington event can emerge. During this massive solar storm, people in the 19th century experienced one of the strongest geomagnetic storms of modern times. The sky appeared to be ablast with a play of colors, and flashes were flying from the juvenile message establishments. The spillage of normal molecule streams into the Van Allen rings, when sufficiently serious, produces a play of colors that we know as aurora or polar lights. The aurora borealis forms in the north, while the aurora australis makes the southern lights. Normally, these phenomena must be seen in the far north or south. In 2024, the particle siege from the sun towards the Earth was so intense that the northern lights were visible well into the interior of the continents. Some auroral lights were visible as far south as the Mediterranean region. People on the tropical Pacific island of Hawaii saw the display for the first time with their own eyes, and in the southern countries of Australia and even South Africa, people were excited by the strange polar lights. This version should be easier to read and understand with appropriate punctuation added. Let me know if you'd like further adjustments.